Hello, my name is Jared Skeens, and welcome to the Zoom room. Today we want to cover Pure Math 1, Differentiation, Part 2, Tangent and Normal Lines. So when we talked in Part 1, we looked at the mechanics of how to do the derivative. Now in Part 2, 3, 4, and Part 5, we're going to look at applications. What do you use the derivative for? So before we get started, I want to just remind you of something here, and that is as we move into the applications, you need to keep in mind what level you're at, meaning, are you in the original equation, the y equals or the function of x? Are you in the first derivative, which is either dy dx or y prime or f prime of x, function notation with the prime mark? Or are you in the second derivative, which is d squared y over dx squared, or y double prime, or f double prime of x? So these are the notations describing which level you're at. It's very important that you know where you're starting from and where you want to go. If you're going down, like from y to y prime or y prime to y double prime, then you're using the derivative. If you're going up, that will be integration, which we'll get to in the next unit on integration, okay? So first you need to pay attention to which level you're on. Second thing you need to pay attention to is the application, or what that level can be used for as far as information. So your original function is where you find coordinates, that is the x, y value of a particular point. Anytime you're looking for coordinates, you need to find that from your original function. The first derivative is to find slope. Now this video and the next two videos are all going to be about different applications of the concept of slope. So this particular one focuses on tangent and normal, which we'll get to in a minute. If later in one of the future videos, we'll also talk about the second derivative, which has to do with minimum or maximum points, that is low or high points on the graph. Okay, so you need to know which level you're on and what kind of information you are working with or toward. You know, which level helps you get that information. I should also point out, in part 1, I was focused mainly on the mechanics, that is how to carefully execute the derivative formulas. And as I look back, I think I kind of forgot to put in some of the notations. Like I put the y function, and then we did the mechanics of how to derive it, and I forgot to put the like y prime in front. So sorry about that. We need to pay attention to both. We need to make sure our notation is correct so we know which level we're on, and we also need to make sure our mechanics, how to execute the formula, is correct, and we also need to know the application that we're working with. Each application has a little different focus to it, okay? So this is kind of a general map of what we're doing. Now let's get to our specific application for this video, and that is tangent and normal lines. Meaning, when we have a curve, as represented by this red line here, when you have a curve, the derivative allows you to find the slope of the curve at a particular point. So if we're looking at point P here on the graph, the derivative of the function of this curve evaluated at the x value, okay, remember we evaluated it for the x coordinate. So you take your y function, you derive it, you plug in the x value, and that will give you the slope at that particular point, point P. That's what we looked at in video part 1, okay, the part 1 video. Now we want to see how else can we apply this concept of slope. Well, if we have the slope at that particular point, then that means there is a tangent line that comes up to the curve and touches at the same point. So this tangent line comes down, and tangent means touches at only one point. And when our tangent line is touching point P, then that means our equation of the tangent line has the same slope as the curve does at point P, okay? So instead of talking about the slope at a point only on the curve, we're now talking about the slope of the line that is tangent to and touching that same point. So since we're dealing with a line, we're now thinking in the y equals mx plus c mode. So this tangent line, the slope of that tangent line will be the same as the slope of the curve at point P. Normal, when we talk about the normal line, and maybe you may or may not have run across it in math yet, but if you're taking science, specifically physics-related science or math related to physics, you will run across this normal. Normal means perpendicular to your plane, or in this case, to the curve. So when you see normal, you want to think perpendicular slope. So tangent, you're going to think same slope, and normal, you're going to think perpendicular slope. You still start with the function, you still do the derivative, but now you're going to apply it to the slope part of a linear equation. So here we have our first example. You have a line, 4y equals x plus c. This line is said to be tangent to a curve. The curve is y squared equals x plus 3. And it's tangent at point P. So the instructions tell us to find c, that is this missing value in our linear equation, and also find point P. Now it's very interesting, these questions, because Cambridge has this question for us. And there's actually a couple of different ways you can solve it. If you wanted to, you could go back to your quadratics information. And remember, in quadratics, tangent also means touches at one point. If it touches at one point or has one solution in common, it means you can use the discriminant, b squared minus 4ac. So if you did that method, if you used the quadratics unit and you followed the discriminant, you would put this equation into this one, you would set it up like a quadratic, you would follow the discriminant, b squared minus 4ac equals 0 for one solution, and then you could solve for c. Once you have c, you can then do simultaneous equations and find point P. So you could actually turn this into a quadratics question instead of a derivative question. But since we're in the unit of differentiation, we want to solve it a different way. So if we're going to solve this using derivatives, we're going to find point P first. okay? So what I'm going to do is we're going to find the derivative here of our curve, but I want to rearrange it a little bit. So y, square root both sides, because we want it a function of x. We want it y by itself. So this would equal y equals the square root of x plus 3, which equals, remember, if we're going to do derivative, we want to write it in exponential form. So this becomes x plus 3 to the 1/2 power, okay? Now, when we do this, we now can write it in notation, our derivative notation. We're just going to use y prime. Multiply the 1/2 to the front, subtract 1, and then do the derivative of the inside, which the derivative of the inside is just 1. So we get 1/2 x plus 3 to the negative 1/2, like that, okay? So now we're going to take this, and we could write it so that it looks a little bit better. For example, this could equal 1/2 times the square root of x plus 3. We wanted to. And we need, this is, remember, slope. Well, how can we figure out the slope? Well, we're told that the tangent line, they give us the equation. Sometimes they want you to find the equation of the tangent line. In this case, they have given us the equation of the tangent line, meaning we can find out what the slope is supposed to be. So here we have 4y equals x plus c. Let's rearrange that to y equals, divide by 4, 1/4 x plus 1/4 c. So here we can see that the slope is 1/4. The slope of our tangent line is 1/4. Okay, here's our tangent line, it says tangent line, here's the equation. Our slope is 1/4. That means the slope at P is 1/4, and here's the equation of the slope. So what we can do is we can take this, here's our equation for slope, and set this equal to 1/4. In other words, this is the answer to this, so we can find x. In part 1 of the video, they gave us the x value to plug into it, and we found the slope. Now, we find the slope from the tangent line and set the formula equal to that so that we can find the x. So we're working backwards from what we did in part 1. So now you just cross multiply, and when you cross multiply, you get 4 equals 2 root x plus 3. Okay, so now we want to divide both sides by 2. So we get 2. Now let me keep it over here, because we're going to do something else over there. So 2 equals root x plus 3. Now square both sides. Get rid of that. So we get 4 equals x plus 3. Subtract 3, x equals 1. Now, that's the x coordinate. And notice one of the things we're supposed to do is find p. The order in which you do them depends on the method you choose. Like I said, if you turn this into a quadratics unit and you did the discriminant, you would find c first and then find point p. So since we're using the derivative to find it, we're finding point P first, and then we'll go back and find C. So this is the x coordinate of point P. Remember, when you're working with coordinates, you work from the original function. So what we want to do is we want to take this 1 and we want to plug it into the original function. Now this is the original one, but this is the same thing, just with y as the subject and y is what we want to finish the coordinate. So if we plug 1 in here, 1 plus 3 is 4, square root of 4 is 2. So our y value is 2. If you plugged it up here, you'd still get 4, and then the square root of 4 is plus or minus 2, but we're looking specifically for the positive 2 in this case. So 1 and 2 is our coordinates. So we already have the answer for P. Find P, 1, 2. Now remember, point P is on our tangent line. That's why we know that the slope of point P is the same as our tangent line, okay? Because the tangent line shares the slope of the point on the curve. So now we need to find C. To find C, you need an x and y. We now have an x and y, so we can plug this in. 2 equals 1/4 times 1 plus 1/4 C. So 2, since we're dealing with fourths, I'm going to change it to a fraction. That's 8/4 equals 1/4 plus C fourths. Multiply everything by 4 to make sure to get rid of your denominator. So now we get 8 equals 1 plus C, subtract 1, C equals 7. Okay, so we found C, and we found point P. So remember, what makes your ability to be successful is your ability to correlate information. So you have to correlate what level you're on, the mechanics of how to get there, that is following the procedure and executing your derivative formula correctly. So you need to know what level you're on and what information the level provides for you. Also, you should be able to solve this through quadratics or through derivative. It really doesn't matter which one you do. You just want to be efficient at whichever method you choose. You don't always have a choice. In this case, you did. So again, make those mental connections. The more connections you can make, the better off you'll be at recognizing these things on your own. So let me set up a different example. Okay, here's our second example. Again, we're given a line, y equals ax plus b. It's said to be tangent. Okay, so you're looking for that tangent normal. So here we see tangent again. And to this curve, y equals 2x cubed minus 5x squared minus 3x plus c at the point P, which has the coordinates 2, 6. And we are to find the values of A, B, and C. So again, remember where you're at and what you want to do. Well, we want to find C, and C is in our original equation. And when you're dealing with your original equation, you want coordinates. And guess what? We have coordinates. So we can just go ahead and we can plug this coordinates directly into here. So we get, here's y, 6 equals 2 cubed is 8 times 2 is 16 minus 2 squared is 4 times 5 is 20. Then 2 times a negative 3 is a negative 6 plus c. So we can find c directly right away because we have the coordinates and we have the original equation. So if we simplify this a little bit, here we have 6 equals 16 minus 20 is a -4. -4 minus 6 is a -10. So that means C equals, add that to the other side, 16. So there's one of our answers right there, because we know that coordinates deal with the original equation, okay? Now we want to move on into slope. Notice here, A is a slope, so we want to find slope. So what we're going to do, so we're going to take the derivative, because we want to find A is slope. So we're going to put y prime here. So again, multiply to the front. So that's 6, subtract 1, 6x squared. These are term by term, and it's not the expanded form. This is just normal terms. So 2 multiplied to the front is -10. Subtract 1 gives us x. 1 multiplied to the front is -3. Subtract 1 is 0. The x cancels. And a constant derivative of a constant is just 0. So here we end up with this. This is now our slope, and our slope equals A. Okay, now that we have that, this slope occurs at this point. Now notice we don't have a y variable anymore, but because our y isn't y, it's now dy, okay? So what we're looking for here is the x value. So here we have x, and our x at this point, our x is 2. So we can plug the 2 in here, and when we plug the 2 in here, you could write this as y prime of 2, kind of like a mixture between function notation and just our derivative notation. So y prime evaluated at 2. So your notation is important because it helps you understand what you're doing. You're kind of giving yourself information here. So there's no math here. It's not multiply. It's more like function notation. So 2 squared is 4, times 6 is 24, 2 times 10 is 20, -3 equals A, because that is our slope of our tangent line. So 24 minus 20 is 4, 4 minus 3 is 1, so A equals 1. So there's our second number. So now we have y equals 1x plus b. This tangent line runs through point P, so we can plug point P in again to this line also. Both curve and the line share that point in common. So we're back to coordinates and the original function. This time our original function being the line, not the curve. And we plug our point into that. So we get 6 equals, our x is 2 plus b. And when we get this, we get 6, well, I can finish it up here in blue. 6 equals 2 plus b, subtract 2, and we get b equals 4. Okay, so there's our ABC using the concept of derivatives, which is slope, with either a tangent line or normal line. Now our first 2 examples were tangent lines. Our next 2 examples will be the normal line. So let me set up the next example. Okay, here's our next example. Maybe you recognize this question. We actually did part of this question in part 1, where we looked at just finding the derivative, only focused on how to do the derivative. Now we're getting into still on the same problem, but a little bit more the application. After you do the derivative, it gives you further information saying there is a point P at the x-coordinate of 2. So the x-coordinate of this point P is 2. It doesn't give the y-coordinate. Then it asks the question, show that the normal, so again, that is your clue that we're dealing with a slope issue here. Show that the normal at point P is going through the origin, which is your point 0, 0. Okay, so this normal means we need the perpendicular of the slope. The normal is perpendicular to the tangent, so we have to do perpendicular slope means your negative reciprocal. Okay, so first things first, I don't know if you remember if you have your work from part 1, but we did the derivative. So let's quickly change the form here. Remember, we want to see the exponent. So we bring the denominator up as 1 unit, and since we crossed the division bar, it makes it negative. When you do the derivative, the constant disappears, becomes 0. So this is gone. The negative 1 multiplies to the front, negative 3. Subtract 1 gives us a negative 2. And then don't forget, this is an expanded form, meaning the exponent is not directly on the x, it's now on the parenthesis, the expanded part. So we have to do the derivative of the inside, which is just 2, because the derivative of negative 1 is 0. So the derivative of 2x is 2. So that gives us a negative 6 over, because this goes back downstairs, 2x minus 1 squared. Okay, so that's our derivative. Maybe you remember that from part 1. Now we have an x-coordinate to plug into it. So we're going to evaluate this. We're going to evaluate this slope for when x equals 2. So if we plug 2 in here, we get 4 minus 1 is 3. Squared is 9. So our y prime now is a negative 6 over 9, which reduces to a negative 2/3. And we want normal, which is perpendicular slope. So the perpendicular to this will be 3/2. Okay, so now we have, and remember, this is a line. You should, for tangent and normal, you need to think y equals mx plus c. The slope, of course, is a very important part, same slope or perpendicular slope, but you need to finish the equation of the line. So our normal line will be y equals 3/2 x plus c. Now remember, this normal line also goes through point P. The normal line also goes through point P. This is the original equation for the normal. It's y, not y prime or y double prime. So this is our original equation. That means we can use coordinates, and we have the coordinate 2. We can plug 2 in. We also need the y coordinate. So we can plug 2 into the original here, because point P is shared by the normal and by the curve. Point P is on the curve. It's also on the normal. We're not working with the tangent in this question. So we can plug 2 into here. And if we take y of 2, kind of like function notation again, up here, we get 2 plus 3 over 2 times 2 is 4, minus 1 is 3. 2 plus 1 equals 3. So this is the point 2, 3. Okay, so remember, anytime you're working with coordinates, you're working with the original. Anytime you're working with slope, you're dealing with the first derivative. You also need to pay attention to point P being on the curve, meaning you can plug it into the curve equation, and it's also on either the tangent or normal, so you can plug it into that equation as well, because point P is shared by both. So now that we have the coordinates, we can plug that in here to find our C. So 3 equals 3/2 of 2 plus C. 3 equals, the 2's cancel, 3 plus C, which means C equals 0. So if our Y equals just 3/2 X, okay, there's two ways of looking at it. This is our y-intercept. Okay, the y-intercept is 0. It means it's crossing the y-axis at 0. So, or you could just plug in if x equals 0, then y equals 0. So either the y-intercept is 0, or you plug in x equals 0, you get y equals 0. Either way, therefore, you're at 0, 0, which is the origin. And that's what you're doing. You're showing that the normal passes through the origin. Okay? So we'll do one more on normal and hope that it gets you going in the right direction. Okay, here's our last example for this video. And it says y equals, here's a curve, y equals 1/2, parenthesis 4x minus 3, raised to the -1 power. And it goes through point A, which is the coordinates 1 and 1/2. And the instructions say to find the normal. So here again is our clue that we're dealing with a slope type question. So you know that you need to use the derivative, and it's through A. So first thing we're going to want to do is find the derivative. Why do we want to find the derivative? Because the derivative gives us slope. So when we see normal, we know we're looking for a normal line. Again, remember, tangent and normal are lines. Maybe I need to put up for you here lines. Tangent and normal lines. So you are looking for a y equals mx plus c equation. So find the normal, or the y equals mx plus c, that goes through A. Well, of course, the major component of your linear equation is slope. Slope can be found through the derivative, like we saw in part 1. The derivative is kind of like the calculus equivalent of your algebraic slope formula. So we want to find the derivative. So our y prime, that is our derivative, multiply the -1 to the front. So it's a -1/2, subtract 1, 4x minus 3, now to the -2. And don't forget, this is expanded. We need to do the derivative of the inside, which is just 4. The derivative of 4x minus 3 is just 4. So this becomes a -1/2 of 4 is a -2 over, because this is a negative, meaning it goes down to the denominator, 4x minus 3 squared. And we want to evaluate this, because it's our slope, at x equals 1. Now, just give me a second here to point out something. Coordinates, x and y, can be plugged into your original equation. When you get to the derivative, at least with these kind of functions, later in pure math 3, you're going to get to slope equations that have both x and y in it. But for pure maths 1, you're only going to have slope equations with x in it. So you need to be careful that when you plug this in, you're only plugging in the x coordinate because you only have the x variable. In the original, you have x and you have y. You plug both in. But in the derivative, there's no y anymore. This is a dy. Actually, it's a dy over dx right now. It's not y by itself. So you don't try to plug in the 1/2. You're only plugging in the 1. So when we plug that in, we get a -2 over 4 minus 3 is 1, 1 squared. So we get -2. Now this is the normal line, meaning perpendicular slope. Don't forget normal is perpendicular. Like I said, if you've learned in your science, the normal force is the perpendicular force to the object. If you haven't learned that yet, then I guess you're learning it in math first. But normal is perpendicular. Perpendicular slope, you already learned back in coordinate geometry, is the negative reciprocal. So the negative reciprocal of -2 is 1/2. So now we can find the equation of our normal. Y equals 1/2 x plus c. Now we have an original equation again, meaning we're at y, the original function. We're not at y prime or y double prime. And our normal goes through the point, except now they call it A instead of P. So we can use the coordinates, both the x and the y, to plug in here. We have x and y, x and y. This point is on the normal, so we can plug that in. So we have 1/2 equals 1/2 times 1 plus c. So here we end up with 1/2 equals 1/2 plus c. Subtract 1/2, subtract 1/2, and we get c equals 0, meaning that our normal line is just y equals 1/2 x. The c is an understood 0, meaning this is going through the origin, although that's not what the question is. The question is just find the normal, and this is the normal, the equation for the normal. Okay, so tangent to normal lines, you need to remember you're looking for y equals mx plus c, or they give it to you. Sometimes they give it to you. You need to remember that the slope is perpendicular to the slope at the point on the curve. And to get slope, you use the derivative to find a slope formula. So it's a lot of correlating information together. And again, knowing what level you're on and what information it provides for you. So this is our first of 4 applications of the derivative that you're going to learn. So part 1, the mechanics. Make sure you get those mechanics down. Multiply to the front, subtract 1. Don't forget the derivative of the inside. Mechanics is most important because it occurs at the beginning of the problem. Then the application. So this is 1 application. We're going to cover 3 more applications. So try to organize it, take good notes. And again, thank you for joining me in the Zoom room, and I'll see you again next time.